बर्बादी बताएंगे और जो करूँ तेरा सिर्फ तुझे हंसाएंगे। क्या करे जब किसी से किसी को प्यार हो।
Okay, hello everyone. Am I audible?
Yes, ma'am.
Yes.
Yeah,
Yes.
okay. So, yeah, I was just waiting in case more people are joining, but maybe we can slowly start and people can join as the class continues. So I'll just share my screen. Right. Okay. Okay, so welcome once again to this problem solving sessions that you are having as part of the NPTEL course. I think by now everyone understands what the sessions are, but basically we are trying to get a handle on, doing our assignments and basically solving the basic doubts that come in the course by having this weekly session where you can have a live interaction and solve, like ask about your doubts on the spot. So my name is Zelia. I am a PhD student at ISC, and I've been taking these sessions for last 4 weeks. All these sessions have been recorded, and the videos have been put on YouTube, as well as the slides have been made available. I hope that you have been able to access these things. In any case, I keep a record of this on my website. So if you just go to my website here, you can see that there is a page with all the relevant links, including the YouTube playlist where all the videos are um, uploaded. Okay. And then you also have the slides of the sessions, which are available here. So these are the basically the links that you need to keep. So I'll just put this in the chat. Sorry. Let me see. Yeah. And as always, if you have any questions or queries, please mail me. I do reply to mails as much as I can. And if you have any doubts or any issues with the grading, you can mail me. Even though I am not in charge of that, I can pass on the message to the people. But again, if you have problems with the assignment, grading, or something like that, the best place to do that is the discussion forum. Apart from that, if you have any doubts conceptually in understanding, or you would like me to cover some topic or something like that, then that can be handled by just dropping me a mail, and I'll make the slides according to your doubt. Okay, so with that, we can go to the session. So today we'll be discussing the week 5 lectures, and now, sorry. And now you have kind of moved into actually getting to the actually constructing Lagrangians and, for different kinds of species as they appear in the standard model. Because the ultimate goal is we want to write down a mathematical and physical theory for the standard model. And for this, what we are doing is we're trying to see what kind of mathematical objects we can map the different particles and interactions onto. So, as I've mentioned a few times now, the way that everything in the standard model is dealt with is in terms of group theory. It's like the grammar of the standard model because we write all the interactions and the particles and the interactions between them in terms of group theory. So, in this context, it's important for us, we've been looking at, what kind of groups or what kind of behavior different particles of different spins correspond to, and how to get a group theoretic representation for them, right? So you already last week saw how scalar particles, which are basically particles of spin zero, can be dealt with. So remember that spin is kind of, tells you a couple of different things. First of all, from spin statistics theorem, we know that spin already tells me about the quantum behavior of the object in the sense that whether it's a fermion or a boson, and this directly tells me about what kind of behavior its wave function follows in terms of its whether it's symmetric or anti-symmetric. On the other hand, spin also kind of tells you about the degrees of freedom. So a scalar particle has, spin zero, and you'll today we'll be writing Lagrangians for something like spin one particles, which are photons. For example, are spin one particles which are massless, and of course the Z and W bosons, which control the weak interactions, are also spin one particles. And you'll see that the Klein Gordon equation that we wrote last time for the spin zero particles does not we cannot just use that for the spin one particles, because as we know, they have more degrees of freedom. For example, a photon has different polarizations. So to capture this kind of behavior, it becomes important to cast it into some other form. And that's why, as I said, it becomes important to see what mathematical structure each of the particles and the mediators or the interaction particles, the mediators which mediate the particles interactions, the force carriers, what kind of actual behavior they encode, so that we can write them in the actual mathematical function. Of course, you also started seeing about the Dirac Lagrangian, which corresponds to spin half particles. Again, these are the most important matter particles we know, like electrons, protons, neutrons, neutrinos, quarks. They all are, obey have spin half, so they all obey Dirac Lagrangian kind of statistics. So these are the kind of different things that you've already seen this week. We also saw a little bit about the cosmological constant problem, which is one of the biggest mysteries or unsolved problems in theoretical physics. Okay, so as I said, our goal is to, we want to encode the information about the different particles and their interactions in the standard model in terms of some mathematical equations. And for this, we are writing Lagrangians from which we get the equations of motion and all those dynamic behavior and the dynamics of the particles and so on. So we already saw that spin zero particles are described by the Klein-Gordon equations. Spin half particles are described by Dirac equation or Dirac Lagrangian, as we just said. And spin one particles have two different behavior that they can follow depending on whether they are massive or massless. If they are massless, they obey the Maxwell equations, as we know from the photon. And if they have some mass, then they obey something called the Proca equation. And these two result in two different kinds of behavior in terms of polarization and other things. So we'll just quickly look at that behavior again. Another important thing is that when we start to talk about particles in the standard model and their interactions, it's not enough to use, quantum mechanics on its own. We actually have to move to, we can't just use the Schrodinger equation, for example. That's why we have all these new kinds of equations of motion. The actual way in which we can derive these and get these is because these are quantum fields. We have to use quantum field theory. So last week I told you a little bit of a primer about quantum field theory, not very mathematically rigorous. Again, if you want a rigorous course in quantum field theory, that takes an entire, semester's course, or more actually, multiple semesters courses. So for me to try to do that in 1 hour would be not right. But I wanted to give you some kind of, feeling for what quantum field theory is actually about, and that's what we've done here. So as I said last week, maybe I can just pull up the slides. Yeah, so as I said last week, the whole point is that in quantum field theory, we go from the first quantization, which is a realization that particles can behave like waves, which is which is a realization that de Broglie had when he wrote down his, momentum position, momentum wavelength equation, lambda is equal to h by mv kind of equation, to the point of second quantization, where we're trying to take these quantum fields and we're trying to put a particle like behavior onto them. We're imposing a particle like behavior onto them. Of course, it's kind of an oversimplification, because what we are actually doing is something called a mode expansion, where we're doing a complex mode expansion and basically writing the different modes that correspond to different particle momentum states being filled. And we understood this in terms of the harmonic oscillator and its, creation, annihilation operators, and all those things. So in that way, we were able to cast a wave problem into a particle problem, and that was the insight that was there, right? So this is the kind of the machinery that you follow when you want to quantize a classical field to form quantum field theory. So the basic idea is something called canonical quantization. This is again from the book Quantum Field Theory for the Gifted Amateur, which I borrowed much of my lecture last week from. So as I said last week also, This is not a QFT textbook as such. It is simply a guide for, getting some intuition and some nice physical intuition for these things. But an actual quantum field theory book will go into the mathematical details in much more rigor. So you should follow that. But I think as a first step, this is a good enough book to follow. So this is from their chapter on canonical quantization, which is basically how to get a quantum field theory or how to quantize a classical field theory in order to obtain a quantum field theory. So you first write down a classical Lagrangian density in terms of the fields. So again, this is the part that requires a lot of information because you need to kind of think about what are the Lagrangians that are corresponding to different interactions or different kinds of particles. I think in the lectures it's been mentioned that the kind of mantra that we follow when we write things for the standard model is if it is allowed, which means that if it's an allowed term but in terms of its symmetry and mathematical consistency, Lorentz invariance and other things, it should be part of the Lagrangian. So that's kind of the idea that we also follow here. That's how you write the equation for, the Lagrangian for the Klein-Gordon equation, for example, or the Dirac equation. We try to form these covariant terms, Lorentz covariant terms, which means that they obey Lorentz invariance. And from that, we try to write down, gather these terms and write the equations. Okay, then we calculate the momentum density, work out the Hamiltonian density in terms of fields. Now you treat them as operators, impose commutation relations, and expand the field in terms of the creation annihilation operators. Essentially do a mode expansion. Like when you solve the Klein-Gordon equation, you get this wave packet equation, and then you can do a mode expansion that corresponds to different modes that the solution can take. And that is it. There is a little bit of subtlety in terms of the Fermi Dirac versus Bose-Einstein statistics, but I leave it to you to read that from any standard quantum field theory textbook. Okay, so I'm going to reuse a few slides now because we are going to build up to writing the Maxwell Lagrangian, which is of course the Lagrangian for spin one massless fields like the photon. And then we are also going to be writing down the same massive analog for that, which is the Proca Lagrangian. So remember that if you want to write a covariant formulation of the Maxwell equations, if you just recall the Maxwell equations, we cannot just use E and B. And the reason why we can't use the usual electric and magnetic fields when we write the Maxwell equations in a Lorentz covariant form is because between two inertial reference frames, the electric and magnetic fields actually get mixed up. So you can see that, what you interpret as a zero magnetic field in one frame can actually have magnetic field in another frame, right? This is very easy to understand because you know that only moving charges produce magnetic fields, but we also know that an object which is at rest in one frame may very well be moving in another frame, right? So that means that the object or the not really the object, the charge which is having no motion in its frame, that will not have a magnetic field in that frame, whereas in the frame where it is appearing to move, there it will be corresponding to have a magnetic field, right? So this is why electric and magnetic fields cannot be used as such when we write a Maxwell Lagrangian, because they are actually mixed up through Lorentz transformation. And so we have to construct a covariant means basically same in all the frames. If you want to write the Maxwell equations in a covariant form such that they are not frame dependent, then we actually need to construct a new object, which is this F nu nu tensor. And this basically contains the information of all the components of the electric and magnetic field. It's an antisymmetric tensor. And what you see is that eventually all the Maxwell equations can be rewritten in terms of these two tensor equations itself. Okay. If you're not very familiar with tensors, please brush them up. I'm sure you know about four vectors from your special relativity classes. Tensors are, generalization basically of writing down things in terms of, different components. And this Einstein summation convention is when you write a tensor indices, when you repeat them in an equation, you typically sum over them. Okay, so you can just brush up about this, but the main point is that the main idea I want to drill here is that even though the Maxwell equations, as we are familiar with them, are written with E and B and all those things, we cannot continue the same kind of notation when we try to write it in a covariant form, because of the thing that I mentioned, which is that under the Lorentz transformation, these fields get mixed up. So we really need to look for um, this f mu nu kind of thing, and now it becomes a tensor equation which is valid in all frames equally. It's not frame dependent. Okay, so you can see that Gauss law and Ampere's law combine to form this equation, and the Faraday law of induction and Gauss law of magnetism, del dot b equal to 0, that combines to form this equation. And you can actually do a kind of a uh, verification of this fact by doing a component based component kind of uh, component by component. You can try to expand these equations and see if this is indeed true. You can also see that f mu nu can be also written in terms of the four vector potential. So the vector potential is A. Usually we write it as del cross A is equal to B, and the four vector potential is usually, just a four vector along with the scalar potential, which comes in the electric field equation. And you can see that the electromagnetic tensor, apart from constructing it in terms of the components of the electric and magnetic field, you can also take it from this kind of del mu a nu minus del nu a mu form. You can also confirm this by just writing down the terms explicitly or with some fancy tensor algebra. So the point is that, as I said, the main point of all this is, if you are going to write a quantum field theory, as I said, quantum field theory itself comes from the fact that we need to have theories which are consistent with both quantum mechanics and relativity. And if I want to have a theory that's consistent with relativity, it must be covariant. Okay, it must be Lorentz covariant, which means that it is the same in all frames. Whenever you write down a Lagrangian in the standard model, it cannot be frame dependent, right? We have to write down fundamental equations which are frame independent. So that's why you try to construct these Lorentz invariants or Lorentz covariant terms, depending on what is the kind of field description you're looking for. But whatever you write, it should be the same in all frames. It should not be frame dependent. So this is kind of like the first exercise in writing a frame invariant or a covariant theory. So you can write that we may derive Maxwell's equations in the vacuum from the Lagrangian this, and remember that when you write del mu a nu, del nu a nu, this is basically your f mu nu kind of term only. And yeah, you can just expand this and see that this can also be written in terms of f mu nu, because f mu nu has this form. So, yeah, notice a funny minus signs. This is to ensure that the kinetic terms for AI are positive using the Minkowski metric. So, if you ever see any differences in how equations are written, just check what is the metric convention they use. The time signature of the metric can either be negative for the time coordinate and positive for the spatial coordinates, or the opposite, positive for the time coordinate and negative for the spatial coordinates. It usually brings some small minus signs here and there, so you can just check. It will usually be written wherever you're using it. So here you can see that the Lagrangian comes out to be here, and Maxwell's equations do follow. If you write the Euler-Lagrange equation corresponding to this Lagrangian density, from that you can get the equations of motion, and you can see that that's exactly the del mu a, f mu nu, and f mu nu, they are defining like this, again, this exercise. And you can check that this reproduces the Maxwell equations in a vacuum. That is these two equations. Using the notation of field strength, we can write the Maxwell Lagrangian up to an integration by parts in the compact form of this. Okay, so this is basically the Lagrangian that we have. So here also this is basically the Maxwell Lagrangian that we have to have. So you can see that it's written in terms of f mu nu. Again, as we discussed, the reason why f mu nu has to be used when we write the Lagrangian is because this is actually the frame invariant quantity that we require. Okay. So you can see that the classical Lagrangian of electromagnetism is given here, with f mu nu having this term. And under Lorentz transformations, you can the vector field transforms in this form. So this lambda mu nu is kind of like the Lorentz, the SO3 matrix that corresponds to the Lorentz transformation, right? So you can also, usually we write Lorentz transformation in terms of some equations, but you can also encode it into a matrix, and that matrix belongs to the group that the Lorentz transformation belong to is a special orthogonal matrices of order 3 comma 1. So that I think has been discussed in the lectures as well. So this is basically how the field transforms. So everything looks good so far, but so this is all until now it's all classical fields, right? We have not yet quantized the theory. So now let's try to quantize the theory. So everything looks good so far, but a puzzle arises when we try to quantize this theory. We know that the photon has two independent polarization states corresponding to the two possible helicities of a massless particle. So again, remember that helicity is kind of like the component of spin. Uh, with the momentum, right? The dot product of the spin and the momentum. So a particle can either travel, if it's a massless particle, it can either have positive and negative helicity, like a neutrino or something. Of course, neutrino is the wrong example because neutrinos are only left-handed in the standard model. But yeah, basically there are two possible helicities of massless particle. We know that the photon has two independent polarization states, but when we write it in this form, then obviously a mu we know from its definition that it's a 4 vector which transforms as a 4 vector under the Lorentz transformation. So it has 4 components. So then it looks like the theory has 4 particle states. So this is the kind of puzzle that we have. So before, when we wrote the Klein-Gordon equation and other things, that was a scalar particle. So there weren't any like components that we had to worry about, right? It was just a single degree of freedom, and that's why it was a spin zero. Now in spin one, it turns out that the particles are vectors now, and not only vectors, they are 4 vectors in line with special relativity, which transform as 4 vectors in the Lorentz transformation as well. So in that sense, it looks like now we are at a impasse because we know the photon is massless and it has two polarization states, but the number of kind of states that are there in the Lagrangian is 4. So how do we get rid of these two spurious degrees of freedom as we see it? So there is where this very important concept of gauge invariance comes in, and gauge invariance is another very brilliant insight that brought us to the standard model that goes deeply into why the standard model is the way it is. So let's, before we go into gauge invariance and why the photon ends up with two states, let's take a brief detour and let's first look at massive spin one. So the photon is obviously massless, but there are also massive spin one particles. If you just look at the vector, so the force carriers itself, the W and Z bosons, which are the force carriers of the weak interaction, they are massive, they are massive particles, right? So in that case, you can see that the Lagrangian looks like this. So note that there is an extra term which comes because there is a kinetic term corresponding to the mass of the particle. Obviously, in the photon case, because m is 0, this term itself was not there. Now, you can always write this in terms of this kind of term. This is basically just in terms of, you're just defining Z mu nu in terms of this. So here, Z mu nu is kind of like your photon tensor. So it's the same thing. It's just that we are calling it by some different name because we are in a different kind of regime in terms of the standard model. Okay. So, right. So this is how you can see that the only new thing here relative to electromagnetism is the mass term. So I got these notes, by the way, just in between. I would say that David Tong's QFT notes has a nice discussion of this, as well as this set of notes from David Morrissey. You can try it looking at these. I just got them online. I've linked them in the slides. So if any of the stuff looks a little difficult, or I'm just condensing it because you've seen it in the lectures, but if you want to take a closer look, I've given the link in the slides itself. Okay. So the equations of motion implied by these Lagrangian are, so again, you go through the same machinery where you write this Euler-Lagrange equation and try to get the equation of motion, and this is what you end up with. And because this side is 0, so I can just apply a derivative to both sides, and that means that the derivative should be 0, right? So the derivative of this ends up being 0 only, but the derivative of here, you can see that there is this m square del nu z nu term, right? So this drops out. You can try looking at it and see how it drops out, because you can try doing it. But here this doesn't drop out. This results in this condition m square del mu z nu is equal to 0. Okay. So from this, you can see that this gives us a constraint, right? So this gives us a constraint on the 4 degrees of freedom that we know comes from the vector. Now we have one which is constrained, and that leaves us only with 3 degrees of freedom, or 3 polarizations for a massive spin one particle. And this is exactly what was shown in the lectures also. So this is from your lecture notes. So I hope you guys have been able to access the lecture notes. These are writings that Nirmal follows when he teaches the class. So it's there on the course website only. If you go to lecture materials, you can get it. And I think you'll be able to find it easily. So basically, you can see that if you put del mu on the equation of motion, here the notation is slightly different, but basically you have some del nu squared kind of term, which, this whole thing cannot be 0. So this whole thing cannot be 0. So obviously del mu z nu has to be 0 kind of thing. And this removes one extra degree of freedom. So this is a Lorentz invariant constraint. Again, this does not assume any frame of reference or anything. Here, everything is written in terms of 4 vectors and tensors. So this is not really a constraint that's coming in one particular frame and not in another. This is true in any frame. So that's why you see that this degree of freedom is removed. And this is how this SO13 kind of convention also can be explained. You can look at the lectures for more details. But the point is now that we can, we have 3 kinds of motion that you can have in the, sorry, polarization that you can have in terms of the massive Procca-Lagrangian. So this is what is called the Procca-Lagrangian, because it's a spin one Lagrangian, but with mass, right? Of course, the massless spin one is, of course, the photon. So we can follow a similar kind of uh, uh, similar kind of philosophy to go through what this Maxwell Lagrangian should be. Of course, there is no m squared term because there's no mass in this case. But again, remember, we know that because photon is massless, it can only have 2 polarizations, basically one corresponding to spin and helicity aligned, and the other will be the spin and momentum are anti-aligned. And you don't have any longitudinal polarization corresponding to the mass, which is the case in the case of a massive particle, right? We don't have that kind of freedom here. So we should end up with something, even though we have 4 components, we should finally end up only with 2 independent components. Okay, and that's what we'll see how that comes about. And as I said before, this all comes down to this concept of gauge invariance. So you can see that we can write Maxwell's equations in a form equivalent to, okay, whatever. So Maxwell's equations can be written using F mu nu. This we already know. This is, the 2 equations. That's all fine. You can also write a 4 vector continuity equation for the current and the currents and current, charge density, whatever it is. Okay. So now you can see that in terms of charge density, in terms of this equation, you can then, from this equation, if you substitute 3.9 and 3.12, then you obtain something like this. And here again, if we apply del mu to both sides, then you can see that del mu a mu is equal to 0 can be okay, sorry. By applying del mu to the gauge transformation expressed in by equation 3.8, okay, 3.8 is not here, that's fine. We can see that for an appropriate choice of the function chi such that del mu a mu is equal to del mu a chi, then one can fix this. So this is called the Lorentz gauge. This is something that you would have done in your classical electromagnetism as well, which is that, you can always add like a scalar field to the gradient, because you can always add a constant term to your potential, because anyway, the only thing that matters is the gradient of the potential or the curl of the potential. The potential itself doesn't matter, right? So that is what is called this Lorentz gauge. Okay, so maybe I can just show you, because I got this from some lecture notes and somehow the whole thing is in there. So yeah. So, for example, you can see that the potentials that determine the E and B fields are not unique. You can always add this term del mu chi to the potential and you will get the same E and B. So, this is what is called gauge invariance, where you have this freedom to add an extra term to the potential, the four potential, and you still get back the same physics, right? The physics is not dependent on chi. So, one choice of chi that you can do is that you can choose that del mu nu is equal to 0 based by fixing some value of chi, and this is what is called the Lorentz gauge. Okay, so by fixing the Lorentz gauge such that the derivative of del mu nu is equal to 0, we can then simplify this equation in terms of this. And remember this, again, when I do this step, I'm not introducing any new physics to this question. Okay, you might think that, oh, I'm fixing chi, doesn't that change the physics of the system? No, the whole point of gauge invariance is that I have this spurious thing. I have this extra, you not really degree of freedom is maybe not the right word, but I have this extra control that does that, how much ever I change that control, the physics of the system doesn't change, right? How much ever I change chi in this equation, the electric and magnetic fields at result the Maxwell equations, the behavior of charged particles is not going to change. So I have the freedom to choose chi to be whatever I want. Okay, so that's what gauging invariance means, which is that the physics of the system is not dependent on that particular parameter. So it's very much related to symmetries and the other things we were talking about in the beginning, but you will see more of that later. But the main point is this, that we are going to fix the gauge such that del mu nu is equal to 0. This is called the Lorentz gauge. And here I have just made a choice of what chi should be, and that does not affect my physics in any way at all. It's just that the way we have defined and the way we have written down this mathematical theory, there ends up being this, knob that we can turn however we want, and that does not affect the physics. That's the main takeaway that you have to have. So in this gauge, you can write the equation 3.12, which is basically this equation, right? The source equation, the Maxwell equations. You can write it in this form. And yeah, when you do that, you can see this. If you solve this in a region with no electric charge, you can use a trial solution, which is this. This is basically the Laplacian. No, this is not Laplacian because it has a source. So it's like del square, right? And then it's kind of like the Poisson equation, and where the not really Poisson, it's like D'Alembert or something. So where the four vector polarization will be a function. So you are just writing this trial solution. Here, this epsilon of mu represents the four vector polarization, which is a function of the four momentum, which is to be determined, and n is some normalization. And if you solve this in a region without sources, which means this J mu is equal to 0, J nu is basically just the charge density and current density together as a four vector. So it just represents what is the sources in the question, which is the charges and currents that are sourcing the electric and magnetic field. If we are solving it in vacuum, of course, J nu will be 0. So if you put that back, you can get this to be the equation. And equation 3.18 is a solution provided k square, that is k mu k nu, is equal to 0. And this allows one to interpret an excitation of the electromagnetic field as a photon with zero mass, because we finally get the four momentum to be 0, which is true when we have zero mass. And using equation 3.18 with the Lorentz gauge condition. So this, if we put in the Lorentz gauge condition, which is that del mu a nu is equal to 0, so just take del mu a mu, del mu on both sides, then you can see that del mu a nu is something proportional to k mu e mu, which is, you can just expand in terms of the space, temporal and spatial components. And thus, in this gauge, the four momentum is orthogonal in the sense of the four vector product to the polarization vector. The polarization vector E mu has four components, but because of this constraint, which is this equation that we've written down, only three of them are independent. Okay. But yeah, but then as we know, there are not three polarization, there are actually only two polarizations. So that means that there is still some spurious, A mu is not fully fixed, right? We already saw that a mu was not fixed because I could always add this del mu chi, and none of the physics was changed, right? So I found that there's one gauge degree of freedom, and that led to this one constraint that removed one spurious degree of freedom. If I now do the same kind of funda, I see that del mu a mu is also simply not fixed, because I can always add the 4 vector gradient of a scalar function to a mu, and because uh, divergence of a gradient is zero, right? That means that this is also a solution of AMU. So again, I have this extra knob. Before it was chi, where I could always add chi to the problem, and that would still give me the same electric and magnetic fields. Now I am able to add this extra function, which is del mu lambda, and lambda, as long as lambda satisfies some particular equation, I can always twist the knob and I can still get the same physics. So that means that there is one extra degree of freedom that we have not accounted for. And you can say that suppose in a given Lorentz gauge, the vector potential has some non-zero divergence, say del dot A is equal to this. Then we can carry out a further gauge transformation according to this, and with a function that lambda, such that lambda satisfies del square lambda is equal to G, so that by construction we get del dot A is equal to 0. So basically we try to fix it such that the divergence of A is also 0. So here we have fixed it such that del mu a nu is 0, and here we have also fixed the del dot A dash is equal to 0. That is like the spatial components basically. And you can see that this is what is called the Coulomb gauge. Okay, so the further requirement of zero divergence of this vector potential represents one more constraint. So in the Coulomb gauge, the polarization vector only has two independent components. So one of the components gets removed because we have this Lorentz gauging of the system, and then one extra component gets removed because of Coulomb gauging of the system. So again, don't I'm not saying that only if we go to some particular special condition that these degrees of freedom are removed. No, that's not what I'm saying. We know that the photon generically has two polarization, and remember that whenever you write a theory in the standard model, it is a covariant theory, it is not frame dependent. Gauge invariance is something a little different than Lorentz invariance. Gauge invariance tells that no, it's not about transforming between frames, okay, like Lorentz invariance is. Gauge invariance is that your theory is written in such a way that one of the parameters is not fixed completely. I can always add some arbitrary value or some arbitrary function to it, and it still gives me the same theory. So that gauge invariance basically tells me about the non-uniqueness of the theory, right? So that means that there are some, even though the theory looks like it has 4 degrees of freedom, because the theory is not unique, it actually shows up some extra degrees of freedom that are not physical. And the way that we deal with that is we gauge the theory, we get rid of these non-unique things, we get rid of these gauge transformations, we do gauge transformations such that we are able to do away with these things, and that gives us constraints, and those constraints tell us that okay, these there are at least two constraints on the 4 vector that represents a photon. That tells me that there are only actually two independent polarizations that the photon can have, and this we know, again, it's a massless particle, so it can have two kinds of polarizations, and we can represent them in some particular basis like this. Okay, so remember that in the case of the massive particle, what happened was we still had some gauge invariance. This is also kind of like a gauge invariance, right? Because this tells me that del mu z nu 0, or this is not a gauge invariance as such, this is more of a condition. So when we have this condition, we saw that there's a constraint, and that removed one of the degrees of freedom. Okay, so you can see that this constraint removed one degree of freedom. So here what happened is the constraint came because we have these gauge invariance, and the gauge invariance comes because the theory, or A knew the vector potential was not unique for the system. We are always able to add something to make sure that it's still the same theory. So when we get rid of all those non-unique elements, we are left back with two polarization, which is exactly what we know about photon. Okay, so that's basically what's given here. This you saw in your lecture as well. So again, you can see that equation of motion is basically the D'Alembert del mu ai is equal to 0. You have the Coulomb gauge, which fixes the divergence of the spatial part should be 0. The Lorentz gauge, which says overall del mu a nu should be 0. And by both, so each of them, so the Coulomb gauge gives me 1 degree of freedom to be removed. The Lorentz gauge condition gives me 1 degree of freedom to be removed. And then when you do the mode expansion, you can, so basically you can also write this in terms of the mode expansion, which is again what we actually do in a quantum field theory. You can see that in the equation of motion, I can always fix the gauge to be some particular value and get rid of these extra degrees of freedom. And finally, I am left behind with only two polarizations. Okay, so they can be normalized in whatever ways. For example, you can write them like this. This is only the spatial part, but this you can also write them in this. But the point is there are only two independent vectors. Okay, or two independent polarizations for the photon. Okay, so that is kind of like a review of spin 1 in terms of both the massless and massive Lagrangians. Last week you saw about Klein-Gordon, which was for spin 0 or the scalar degrees of freedom. So again, spin kinds of tells us two things. One is about the degrees of freedom that are accessible by the particle in terms of its the mathematical behavior, and also tells us about what kind of behavior it has in terms of the spin statistics theorem. So you also started looking at the Dirac equation this week, which we'll discuss probably in next week's lectures. For now, let us kind of start solving problems together. Okay, so as usual, let me show the question and then you guys can answer in the chat. Okay, someone said they'll join back in 15 minutes. That's fine. Um, okay. Oh, sorry. Okay. So the first question, maybe we'll just continue and the other people can see it from the recording or something. This is the first question. Which of these is closest to the measured value of the dark energy density? Okay. There are only like few people in the, okay, fine. Okay. So it's not about the energy dense, it's not the energy, it's the energy density. Yeah, okay, fine. Okay, someone says A. A, yeah, okay, good. So all of you are correct. It's actually the measured value of the dark energy density is actually something very small. And this is why it's so confusing that the quantum field theory value, which is based on this concept of 0 point energy of the field, comes out to be something like hundreds of orders of magnitude higher than the value. That is the cosmological constant problem. So here I have a question. So you can see that this is supposed to describe something called an energy density, right? Energy density should have units of like energy per volume, right? But the solution is given in terms of milli electron volt to the fourth. So how come milli electron volt to the fourth is describing an energy density? Exactly. So this is because of natural units. So remember that in particle physics and in high energy physics in general, we use special units where we set the values of h cut and c to be 1. Okay. Yeah, MeV to the third actually converts to a volume. So because the Planck constant and C are set to 1, their values don't, I mean, their units are actually hidden in many of these things, and that's why energy density can be written as milli electron volt to the fourth. So this is very common in particle physics, high energy physics, also in astrophysics to some extent. So if you ever get confused about the units of something, like what I asked you now, you can always try and see. So here the idea is that actually I can put in a swing. So so if I just write h bar c, h bar times c is actually something like 197 MeV per Fermi cube. Okay, if you calculate it in those units, it comes out to be 197 MeV per Fermi cube. But I just told you we are in natural units. So h bar c is equal to 1, right? Okay, sorry, this is latex, so I can't do that. Yeah, which is equal to 1. So that means that, so this tells me basically, sorry. So this basically tells me that you can see that if I just take this Fermi cube to the other side, you can see that one Fermi cube is equal to 197 MeV. Or in other words, basically volume, Fermi cube is basically a volume, right? Femtometer cube. Fermi is femtometer, 10 power minus 15 meters, whatever. It is a length cube, which means it's a volume. So volume just corresponds to energy. Okay, so that's kind of what is happening here. Okay. Yeah, exactly. Energy goes as length to the power of minus 1. Okay. Sorry, I wrote it wrong. Not MeV Fermi cube, MEV Fermi. Ah. So MEV Fermi, which is equal to 1. MEV per Fermi. So basically, then 1 Fermi is equal to 1 by 197 MeV. So then, something like MeV per Fermi cube, which is what is energy density, E by V, would be nothing but MeV to the power of 4. Okay. So here I wrote it in terms of mega electron volt, but yeah, you can write it in terms of whatever units, right? You can write it as energy and length. I just wrote as mega electron volt. Of course, this is milli electron volt. The point is that something with the dimension of energy to the power 4 has the same units as energy per length cube. Okay, I thought it's important to talk about this because these are the things that we understand during the lecture, because it's kind of, or people don't explain during the lecture because it's kind of understood, but then doubts show up later. Okay, next question. Why does the 0 point energy become a problem for quantum field theory but not for quantum mechanics? Okay, someone says C. Okay. Particle mass spectrum is basically like just like how you have an energy spectrum, because energies are equivalent to mass, you can also have a mass spectrum. So remember, we are exciting different energy modes, right? When we write something in terms of a quantum field theory, when we do a mode expansion, we are basically writing different energy modes. But you can also think of them as exciting different mass spectrum modes. That's what's happening. It's basically because all of them are uh, different. Okay, so I think two of you said C. C is the correct answer. So basically, in quantum mechanics, we have this, we don't have to integrate overall space or anything like that because we don't deal with Lagrangian densities. We are not dealing with field theories which are stretched over all space, right? We deal with particle space states, and in a particle, even if the energy, 0 point energy is something, that's for that one particle. Whereas in quantum field theory, what happens is we are writing all the Lagrangians to be defined over all of the time and space that is there. And because of that, if there's a 0 point energy or a constant term in the Lagrangian, it's actually integrated over all space. And in that sense, it becomes something that is, gravitationally significant because energy is mass, as I just said, and that can further drive the expansion of the universe. So the problem that lies here is that from cosmology, we can actually measure the value of the dark energy, which is thought to drive the expansion of the universe, and you can see that it comes out to be a tiny value. Whereas if we calculate it based on this concept of 0 point energy, where we are integrating a constant term over, all of space time essentially, then or rather than space time, I would say, or the entire energy spectrum, let's say, or all the energy states that are allowed, then because of this integration, it becomes a very large term which is not matching up with the actual value that we see. So this kind of discrepancy is why this is a problem. The cosmological constant problem comes up. Okay, next question. The Proca equation describes which of these states? Mark all the right answers. So here, because it says mark all the right answers, there could be multiple answers that are correct, or even one answer, right? So it could be one or more than one answer. So write all the correct answers. Okay. Z delta and rho meson. Okay. Someone said Higgs also. Any other answers? B and E. Okay. Okay, maybe I think everyone's answered. We can go to the answer. So the answer is actually the Z boson and the rho. Some of you have said this. So first of all, let's try to think about how we can look at all the correct answers, right? So I just explained the Proca equation to you in the first part of today's class. So as you know, Proca equation is for massive spin one particles. So I already know spin one particles are baryons or mesons. So spin one particles or okay, in other words, spin one particles are fermions or bosons. Yes, mesons, right? So spin one particles, first of all, we know that they are bosons. Because of spin statistics theorem, we know that if it has integer spin, it's definitely a boson. At the same time, we know that baryons cannot have integer spin because they are formed with three quarks together. So when three quarks combine, it can either have spin half or spin three halves or something like that. So that's why we can eliminate delta baryon right away. Electron is also eliminated because we know it has spin half, because electron is also a baryon. It obeys the Pauli exclusion principle. So we are left with the Z boson, Higgs boson, and rho meson. So here it becomes a concept of you have to know that the Higgs boson actually has spin zero. It's the only spin zero particle in the standard model. And what equation of motion describes spin zero particles? Yes, exactly. The Klein-Gordon equation. So that is the idea. Okay, and rho meson actually has spin of 1. Again, you can look this up later. So these are massive particles with spin 1. The others, again, electron and delta baryon are eliminated because they don't have spin 1. Higgs boson also doesn't have spin 1. But I'm just giving you the funda of when you see these kinds of questions, where you have to multiple answers you have to mark. Try to first eliminate the obvious options, and then you can try to narrow down on the options based on your knowledge. Okay, next question. The Dirac equation describes which of these states? Mark all the right answers. So you can put your answers in the chat. Okay, A and D. Someone says A, someone says. Okay, maybe we can go to the answer. Others also please try to answer. I'll give you a minute if you haven't. Okay, fine. No problem. So the answer is A, it's the electron. So we didn't discuss the Dirac equation today, but oh, sorry. But basically, it was discussed in this week's lectures, and you will be getting into more detail soon. But basically, spin zero particles are described by Klein-Gordon. Spin one is by Proca or Maxwell, depending on the mass. And for spin half particles, we use the Dirac equation. So maybe this week I didn't want to overstuff it. So maybe next week we can discuss the Dirac equation in more detail. But I'm sure it's already been covered in your lectures in some detail. You can go and look there also. So particles which have spin half, so all electrons, quarks, neutrinos, they all obey the Dirac equation. Also composite particles like the proton and neutron, they also have spin half, so they all obey the Dirac equation. So let me just go back to that question. So once again, from just spin statistics, we know that the boson or meson cannot be spin half because it has integer spin. So those options are all automatically eliminated. And the delta baryon actually has spin 3 halves. Okay, you might remember this because we spoke about the isospin multiplicity of the delta baryon recently, where the delta baryon has 4 charge states, right? Delta plus plus, delta plus, delta zero, and delta minus. So that means its spin is actually 3 halves, and that's why it has isospin also 3 correspondingly. Okay. So here the answer is only the electron. Okay, fine. So if the two transverse polarizations of a massive spin 1 boson are 0, 1, 0, 0 and 0, 0, 0, 1, what could be the longitudinal polarization? Okay, someone says D, someone else says D. Okay, so I'll just go to the answer because I see that two people have answered. Yeah, the answer is D. So again, you can calculate this based on, we saw, right, when we derive the polarization expressions for these kinds of spin one particles, you can see that they end up with this k mu e mu is equal to zero kind of condition. So based on that momentum equation, you can kind of derive it. So this corresponds to the mass, the fact that the particle is massive. This constraint kind of becomes completely zero when we look for the photon, as we saw from the Coulomb gauge. Okay, so from the orthogonality condition, and that the fact that has to be normalized to zero, you can actually try to find out the equation. So I have not solved it here, but you can solve it yourself and check. So it has to be orthogonal to the momentum. So from that you get this k mu e mu is equal to zero, and then the normalization just follows automatically if you just normalize this to 1. That's why the divided by m term is coming. Okay, fine. Next question. Mark all the conditions required to obtain only the two propagating degrees of freedom from the field of a massless spin 1 boson. A and C, A and D. Okay, C. Okay. Maybe we can go to the answer. So the answer is A and C. So here, this kind of cheating because there are two things that look very similar, but Lorentz invariance is not the same as the Lorentz gauge. The Lorentz gauge is and the Coulomb gauge are what I told you from before, right? The fact that we have this extra handle on our theory, the gauging of the theory, where I can change that factor and the theory doesn't change. So exactly what we saw in the lecture notes. Basically, I can always fix some chi such that if I add it to the vector potential, if I add del mu chi to the vector potential, it doesn't change. So based on choosing an appropriate chi, I can impose del mu a nu is equal to 0, which is the Lorentz gauge. And then I also have this additional degree of freedom, which comes from del dot A is equal to 0. So only when I fix these two conditions, which is the Coulomb gauge condition and the Lorentz gauge condition, then only I get constraints on the 2 degrees of freedom, and they are spurious degrees of freedom. Only when I get rid of them, then I get the actual two polarizations of the photon. Okay, so that is the answer. I hope that's clear. Next question. The field strength tensor in a Proca theory is, okay, someone says D, someone says B. Okay, someone says don't know, that's fine. Okay. So let's see. Let's see the answers. Okay, so the answer is Lorentz covariant. Okay, so remember that whenever I write a theory in QFT for the standard model, as I said, any Lagrangian I write has to be frame invariant. Okay, it cannot be depending on any frame. That's why when we wrote the Maxwell equations, we wrote it in terms of F mu nu or in terms of A mu and other things, right? We didn't write it in terms of E and B, because E and B, as I showed you, the electric and magnetic fields actually get mixed up when we move from one frame to another. So I always want to write a frame invariant quantity, and that's why Lorentz covariant theories have to be there. So whatever field strength tensor or whatever terms that come up in a theory, they always have to be Lorentz covariant. Okay, Lorentz covariant just means that it doesn't change when I go from frame to frame. That's the reason that we constructed this F mu nu kind of term. And in Proca, you saw that there is a similar kind of Z mu nu, or you can even continue to call it F mu nu actually. The only difference in Proca is that along with F mu nu, like the dual that term, you also have this M squared term, which comes because of the mass. So for example, in the lecture notes I showed you, you can see that this is kind of like the kinetic term, and along with that you have this m squared f mu a nu kind of term that comes from the mass, basically. So we always have to write something that is Lorentz invariant. No, boost is a different concept, right? Boost means when you're changing the velocity alone. So it's like, uh, Lorentz invariance means that there should be both boost invariance and rotation invariance. So there are two kinds of transformations that are there in the Lorentz group, right? The SO3, SO1, comma 3 kind of group. You have both boosts and rotation. So Lorentz invariance means you have to be invariant against both of these things. Okay, fine. Let's go to the next question. The kinetic term of a Maxwell Lagrangian, which of the following? Okay, someone says C. Okay, okay, no problem, no problem. We can go to the answer. Okay, so okay. So the answer is that it forbids a three photon vortex. So as I said, whenever we write a term in the Lagrangian, any Lagrangian, it has to be Lorentz invariant, right? And it has to be derived from Lorentz invariant quantities. So you can see that F mu nu is kind of like is the Lorentz invariant quantity. We constructed F mu nu such that it is, a Lorentz invariant tensor. It's same in all frames, so that we can write the Maxwell equations in like a frame invariant way. So if we are writing any terms in the Lagrangian, it always has to come from this kind of thing, right? So you can see that the F mu nu consists of del mu a nu. It's like something that's linearly dependent on a mu, right? Linear in the sense that only a mu to the power 1 comes in the quantity. So even if I multiply 2 f mu, I only get a mu, some term like a mu. I never get some a cube or a power 4 term. So this tells me that a cube, a power 4 kinds of terms cannot be added to the Lagrangian, because they will not be Lorentz invariant. They are not derived from this Lorentz invariant field tensor. Okay. So that's why self interaction terms like a cube and all are not there, and that forbids this three photon vortex. So in a Feynman diagram at the base level, you can only draw two photon vertices. You cannot draw three photon vertex. This will change when you go to other field theories like QCD, which has a different structure and different symmetry group that you'll see in your future lectures. Okay? Okay, fine. Next question. Antiparticles are in reality what? Okay, someone says B and C. Okay, we can go to the answer. So the answer is not holes in the Dirac or negative energy states. So while these are the ways that Dirac interpreted the solutions, remember that antiparticles are, legitimate particles. They don't have negative energies. Negative energies are there because we write the Dirac equation or whatever. Even in Klein-Gordon, we saw these negative energy states show up, right? But those come up because we have expanded the mode expansion in such a way of having the complex mode expansion. So you have both these positive and negative terms. It's just that the negative terms correspond to antiparticles. Their energies are still positive. They are still physical particles. Physical particles cannot have negative energy states. This Dirac whole picture was there before this existence of antiparticles was really understood, right? People didn't know that every particle has a corresponding charge conjugation pair, which is the antiparticle. There is no idea that electron has positron and proton has antiproton and so on. So that's why this was not very understood. So in reality, what antiparticles are, they are just a simple consequence of the fact that when we do the mode expansion, we have complex fields, so we have to take care of these positive and negative terms. Yeah, exactly, in reality. So those were interpretations that came up early on when we saw these mathematical solutions and we didn't know what to do with them. But in reality, there are no negative energy states or anything like that. Okay. So I think I showed something like this in my last week's lecture also. So yeah. Basically, Feynman and Stuckelberg had given this interpretation that the negative energy states that show up in the solution to Klein-Gordon are particles that are moving backward in time in some sense, in the sense that they're antiparticles, in the sense that their momenta are, instead of being incoming, they're outgoing or something like that. So that's how you think about it. We can discuss this more in detail. Again, I didn't want to discuss Dirac equation also this week because you're continuing to learn about the Dirac equation. Maybe we can discuss these things a little more in detail about why Dirac first of all chose to write the Dirac equation in the first place. It was very much motivated by these negative energy states that showed up in the Klein-Gordon equation. And then Dirac found that if he wants to write the equation, it has to be written in terms of these, complex vectors and other things. And we can talk about this next week, maybe. Okay, next question. Gamma mu, gamma mu. So again, these are the Dirac matrices. If you have seen the lectures, you'll know about them. According to the Einstein summation convention, what does this come out to be? Okay, someone says 0. Someone says C. Yeah, okay. Maybe we can go to the answer. So the answer is actually four, okay? Because remember that the Dirac matrices are, 4 by 4 matrices. They live in four-dimensional space-time. So if I actually normalize the Dirac matrices, it comes to be four. So you can work this out from the commutators, because the Pauli matrices, remember, there are two copies of the Pauli matrices, so to speak, in the Dirac matrices. So they are 4 by 4 matrices. If you take the norm, it comes out to be four times the identity matrix. Okay, so this is a mathematics thing. You can try it out. So again, we can discuss this in more detail next week when I talk about Dirac equation and other related things. Okay, if there are no questions, that was the end of the questions I had. But since we are at the end, I thought before we leave, I can talk a little bit about cosmology. It's not directly related to the course, so if you have to leave, you can leave. But I just wanted to bring in a few things because you spoke about this cosmological constant problem and about dark energy, because cosmology tells us, in many ways, cosmology is also trying to do the same thing that, the standard model is trying to do, which is tell us about what makes up the universe. Just we are looking at it from the biggest scales, whereas particle physics is trying to look at it from the smallest scales. And the cosmological constant problem, for example, is what happens when these two ideas are meeting, but they are not consistent with each other. And that's why it's such a mystery as to why it is like that in the first place. Cosmology is how we know about the existence of things like dark matter and dark energy, which are concepts that are not really incorporated into the standard model of particle physics and require what is called beyond standard model particle physics to really understand them, right? So, if you don't know, cosmology is the study of the universe at the largest scales, over all of time and also space. Remember that the farther you look out into the universe, the farther out in time also you're looking. Okay, because for example, when we look at the sun from earth, because light has a finite speed, right, it takes 8 minutes roughly for the light from the sun to reach us, right? Because of the distance between the sun and the earth, when the light starts from the sun's surface, it takes 8 minutes to travel that distance and reaches the photons that are starting from the surface of the sun. This means that tomorrow, if the sun was destroyed in some freak accident, or some, uh, crazy occurrence, then we would only come to know about it 8 minutes later, right? Because there's a delay between an event happening in the sun and something happening near to us. You can imagine how this delay is only amplified as we move further and further into space. As we move into other galaxies, they can be light years away. So I'm sure you've heard of this term light year. Light year basically tells us about, it's a measure of distance, even though it sounds like a time, because light year is basically the distance that light travels in a year. So if something is 5 light years away, it means that the light from that object takes 5 years to reach us. Okay, so cosmology is basically us trying to study the faraway things in the universe, and in that way, because when we study the faraway things, we also get access to early universe. We are also trying to learn what happened in the very early universe. So we are trying to put these two things together, which is to study both large distances and also to look back in time, more and more. Okay, so this is basically the in history of the universe as we understand it. As probably all of you know, the universe started in something called the Big Bang, and we know that very quickly after the Big Bang there was this huge era of expansion called inflation. You can see that it started at something like 10 power minus 30 seconds after the Big Bang. Within 1 microsecond is when the first particles, neutrons, protons, electrons started forming. Within 3 minutes is when, after 3 minutes is when these neutrons, protons, and electrons started to, combine together to give, the first nuclei and the first particle, first atoms as it is. First atoms form, and then, from their excitations is when we started to see radiation in terms of light. And then, over time, after, around millions of years, these particles grew and grew, and they, start accumulating into things called stars, which are these huge reservoirs of where nuclear fusion was happening, and we could get even more particles and so on. And then eventually the stars, start to accumulate and form galaxies. And here is where dark matter plays an important role, because dark matter, even though we can't see it, it is a provides a lot of mass, it feels gravity, and these gravitational support is what allowed the galaxies to form and stabilize themselves, and so on. Beyond that, 10 billion years ago is where dark energy took over and the universe started expanding, and that dark energy density is what we discussed in the questions as well. So today we are at 13.8 billion years from the start of the universe, and this is kind of the picture that we have. Cosmologists are interested in various things, they are interested in various stages of this. And as I said, because of the way that finite speed of light ensures that as we look further off into space, we also look further back into time. You can actually study things based in that way. You can look back into a particular distance, and from that you can study the processes that were happening at that time. Okay, so this is about the composition of the universe. I think this may have been covered, but basically, the ordinary matter, like what makes up you and I, and everything we know around us, and the standard model, which the matter which the standard model describes, the thing that we are so painstakingly putting together, that only forms around 4%, or rather 5% of the entire content of the universe. Okay, of the matter content itself, 27% is actually dark matter. So dark matter is 5 times the composition of normal matter. A dark matter is called dark matter because it does not interact with light, so we cannot see it at all, not in any wavelength. So it's not like something like something like X-ray where we can't see it because our eyes can't see it. It actually does not interact with any part of the electromagnetic spectrum. And as far as we know, we don't know how it interacts with any other forces as well. People propose things, but we don't have any evidence for it interacting in any force other than gravity. So as I said, dark matter interacts with gravity, it has a mass, and it stabilizes galaxies and other things, and it was very crucial in the formation of these huge galaxies that we see around us. But we still don't know what the nature of dark matter is. So people have different ideas about what dark matter could be, that it could be a particle, it could be tiny black holes, it could be all kinds of things, and people try to see if they can test their theories to either detect or rule out what could be the properties of dark matter, right? So this is about dark matter. The other thing that makes up the universe and kind of dominates it, around 70% of it almost, is dark energy. So dark energy is even more mysterious than dark matter. While we know that dark matter, even though we can't see it in any spectrum, we know that it exists because we know the mass of galaxies, for example, and from their mass we can kind of estimate how much could be the mass of the dark matter. Basically, you can take, because galaxies and other things obey gravitational laws, we can just look at, we can estimate the mass that they obey from the gravitation, and then we can look at what is the mass we actually see in terms of the visible matter, and we can subtract this and we can get an idea of how much dark matter is there in the universe. Whereas dark energy seems to be an inevitable thing that shows up and that is required to actually work against gravity, because remember, there's gravity all over the universe, and it is a component of the universe that actually drives its expansion. So you actually need this reserve of energy that is always pushing out, right? You need, if the universe is expanding, it's because it's coming out from some energy, and that is what dark energy is. So here, this is a plot that you will see in a lot of cosmology textbooks. This is the age of the universe in years. This is the mass density, or yeah, basically the content of the universe. So in the very early era, that matter was very scattered around. They were not, it was not interacting much. It was not clumping together to stars or anything like that. So it was a radiation dominated universe, right? The atoms which were there were, getting excited, producing radiation. So there were photons which were, traveling here and there, and photon and matter were coupled. But as the universe expanded, and the universe has always been expanding, so as the universe expanded, the you can actually calculate how the density of radiation, the density of matter, and dark energy all vary with the expansion or the age of the universe. So as the universe expanded, you can see that the radiation content kind of fell down, because of the wavelengths getting stretched, so they became less energetic. Essentially, you can think of red shifting happening. And at the same time, matter became the more dominant component of the universe. But also matter density also starts going on, and you can think about it, right? Because density is mass by volume. So no matter how much matter you have, if the universe becomes big enough, the density becomes very small. And that's exactly what's happening, is that now you can see that in our current era, both matter and radiation components of the universe are subdominant, and it's actually dark energy which is dominating and accelerating the expansion of the universe. So remember, the universe is not only expanding, it's undergoing accelerated expansion, which means the expansion is getting faster and faster. Okay, that's why the universe's volume as such is growing, and that's why the density of these components are going down. Radiation density goes down faster than matter density because as the universe expands, the light also gets red shifted, its wavelength increases, and when its wavelength increases, its energy also goes down. So you can calculate all these things. Cosmologists calculate these things. They take observations of the universe. I'm not going into the details of that because that's a science of itself, but the point is that they have figured out how much is each thing. And the important thing is, if we need to have this kind of accelerated expansion which we are observing in the universe today, we actually need a constant dark energy. You can see that dark energy doesn't change with time like matter or radiation. This is one of the models that has been proposed, and it has been very successful. Together, this is called the lambda CDM model for the universe. But people do talk about what if dark energy was a varying quantity, and people do theorizing about it. So it's difficult because with dark matter, as I said, we can at least infer its presence based on the fact that from the gravitational masses of galaxies and galaxy clusters, we can get an idea of what dark matter mass is and how much of it is there. Whereas with dark energy, we really only know that it has to be constant so that it doesn't decay off so quickly, and it can still drive the expansion of the universe. But it could also be a very slowly varying quantity. There are many kinds of free parameters there. So these are the things that cosmologists and particle physicists try to research, because remember that in the standard model of particle physics, we are only, in the grand scheme of things, accounting for 5% of everything that makes up the universe. Still, the other 95% is still unknown to us. And that's what people try to do. They try to build models that can be compatible with the stuff that we see to explain the other 95% of the universe as such. So these things are not included in the standard model, and these are the things that what we should address when we try to look for beyond standard model physics. So I'll just show you quickly. Again, this is not strictly there in your course, but I thought since we're talking about cosmological constant problem, we can talk about a little bit of cosmology because it's a very interesting subject. So these are called the Friedman equations, and they describe how the universe expands, or what is the geometry and um, the geometry and content of the universe. Essentially, it's kind of like the standard model of cosmology, if you can think about it. Like we have a standard model of particle physics, we also have a standard model of cosmology, and the equations for that is here. So here A of t is something called a scale factor. Scale factor tells us how big the universe is. So you usually measure the scale factor at a time t with respect to some other time. So for example, scale factor of now when compared to when the CMB was formed is something like I forget what exactly it is, but it's like 1,000 times or something. So, the redshift is 1,000 times. So, scale factor has some relationship. I forget exactly what it is. But basically, between two times, by comparing the scale factor, you can find out how much bigger is the universe now when compared to then, right? Scale factor of now versus some time ago, if is 10 times, means the universe is now 10 times bigger than it was as T1. That's how you think about it. Okay, so this Friedman equations essentially describe how the scale factor, which is the scale of the universe, changes with time based on various matter and energy contents we want to put in our space-time. So this is a equation where we can put in, we can put in the density can be density of matter plus radiation plus dark energy, or you can just put radiation plus matter, so that we can see what is the behavior of the scale factor with only matter and density, with only matter, with matter, radiation, and dark energy, and so on. And it turns out that if we want to get the kind of accelerated expansion that we're seeing now, it has to include dark energy. And dark energy is usually written not in this form, but in terms of this kind of lambda, which is called the cosmological constant. So remember, the cosmological constant problem comes from trying to fix this lambda only. This lambda, from theory, from quantum field theory team, seems to be very big, whereas what we measure is a very small value. So you can go to this website. Actually, there's a blog post which has explained the Friedman equations in some detail, and it's a very nice pedagogical explanation. I'm not going into the details because this is not really a cosmology class, but I thought it's interesting in any case. So basically, this kappa, by the way, is the curvature. Okay, it's the curvature factor of the universe. So with space time, you also have to worry about whether the universe has positive curvature, negative curvature, or flatness. Based on what we know of the universe, it's almost certainly a flat geometry that it follows. Again, these are all very interesting things which I'm not going to right now, but basically, because general relativity is the real theory of gravity, Newtonian gravity does not describe the gravity accurately. And general relativity tells us that space-time curvature itself can be a source of gravity. So we have to take care of the curvature also. Basically, space-time curvature itself, even if there's no matter in the universe, space-time curvature itself can be a source of gravity, because that was Einstein's insight, right? So because of this, we have to also include the matter content. We have to include this dark energy content in terms of lambda. We also have to include the curvature of the universe, because the geometry of the universe kind of tells us how matter behaves or matter moves in the universe. So those are Friedman equations, and then you have an equation of state which correspond to what the different quantities behave like. So matter has its own equation of state, radiation has its own equation of state, and dark energy has its own equation of state. Based on that, you can also write it, and then there's a continuity equation. So these are basically the equations that describe the cosmology or the geometry of our universe, and by solving them, you can understand how the scale factor changes, how the content of the universe changes over time. Okay, so for example, you can showcase the solutions to Friedman equations in a flat universe for different types of energy. So suppose we only have matter in the universe, the equation of state is something like this. The energy density goes as 1 by a cube, and the scale factor, you can see that it grows t to the power of 2 by 3. In a radiation dominated universe, the equation of state has w is basically this quantity. W is 1 by 3, and the energy density, you can see, grows as 1 over a power 4. Scale factor goes as t halves. In dark energy dominated, the dark energy equation of state, what we propose or what we think it is W is equal to -1. You can see that the scale factor grows exponentially. And this is exactly the behavior that we see, which is the accelerated expansion of the universe. That's why we think that this kind of dark energy component is really very important if you want to describe the universe as we know it today. Okay, we know that the universe is expanding exponentially, accelerated expansion is undergoing. That kind of can be explained only if we have a dark energy dominated universe. So now you can understand really these slopes, right? So you can see that matter falls off as 1 by a cube. Rho, a being the size of the universe, you can think of it. Rho falls off as 1 by a power 4, because again, as the universe expands, the wavelengths of light also get stretched, so that energy falls off. So there's an extra 1 by a, whereas dark energy doesn't depend on a at all. It's independent of a, so it just stays constant. And that's exactly what this kind of graph shows. It shows that initially, even if radiation was the dominant part, it falls off with a very large slope, whereas the matter dominated part, it falls off with a less severe slope, whereas dark energy does not fall off at all. It is independent of the scale factor. Okay, so the age of the universe also corresponds to the scale factor, because as time goes, the scale factor changes because the universe is continuously expanding. So you can see that this is something called the Hubble constant, which explains the velocity at which the universe is expanding. It's also related to the scale factor. Everything comes back to the scale factor or the size of the universe. But basically, here you can see that the radiation term dominates when E of t is small. So at the beginning of the universe's history, the matter term becomes significant when this kind of term comes up, and then matter becomes a dominated energy. The dark energy term only dominates at the end, because it's a small value, it's a very small value, as you saw in your lectures also. When we measure it, it turns out to be a very small value. But the reason why it still plays a role is because other components, as the universe expands, the other components contribution becomes smaller and smaller, whereas this component, even though it's small, because it remains constant, it's always there. So this is when the dark energy becomes a dominant form of energy in the universe. So we are currently in a dark energy dominated era because we can measure these things. So I won't go into the details, but there's something called the cosmic microwave background, which is basically this kind of black body uh, uh, curve that's generated by the initial expansion of the universe. We can detect it, and from its power spectrum, we can kind of tell what is the components of the universe that resulted in such a spectrum being produced in the first place. And from this kind of curve, we can also tell how much of each thing should be there, such that we see the properties we see. And that's how dark energy can be constrained as well. Okay, so yeah, so that's a little bit of cosmology. Again, this is not to do with your course as such. I just wanted to include it because I thought it'll be interesting for you to learn about this as well. Okay, so I think that's all I have for you today. So, if there are any questions, I can take them now. Uh, okay, fine. Okay. Thank you guys. I'll just share the links again. So remember, this is my mail ID. Please feel free to mail me if you have any questions. And if you want me to cover, more importantly, if you want me to cover a particular topic in the lecture, you can mail me and I'll include it in the slides. As you see that, I have some space to discuss things. So please feel free to mail me about doubts you have. Other than that, this is my website. In this website, you will find all the links to the sessions, recorded videos of the sessions, and also the slides. Okay, so you can just save the link and you can go and check out this link as it is. Okay, fine. If there's no other questions, then thank you very much for joining, and I hope you have a nice week. I'll see you again next week at the same time. Okay, thank you. Bye.